Hello students. So I am Samin Sahu. So let us continue the previous lecture. In the previous class, we studied about electric potential and potential difference. And today we shall be studying something more about those things, that is electric potential of a point charge. Okay. So let us make the system. So today we are going to calculate the electric potential. So you have been given a point charge and you are to calculate the electric potential of that point charge at a given distance. Okay, just like yesterday's class, electric potential due to a point charge, due to a point charge. So in every classes or every concept previously, what we have studied, that in case of force, in case of electric force, we calculated electric force due to on a point charge, on a charge due to a point charge. Then we calculated the electric field uh, of a point charge. Now we are going to calculate the electric potential of a point charge at a given distance. Okay, so I think this is visible to you. Yes, it is. So let us continue that electric potential due to a point charge. So let us make those arrangements. What are those arrangements? So we have to plot a point charge. Let Q be a point charge. So the plot is here. I think it is visible from this point of view. Yes, it is. So it is a point charge Q. Let me make it closer to me, to this side. So and another test charge, that is Q naught. Okay, this is Q naught. Not now. So we have to calculate the electric potential due to this charge at any point P. If this is a point P, then we are going to calculate the electric potential due to this point charge at this point P. Okay. So I think yes, it is visible. So for doing this, just draw a line along this point such that it joins a straight line. Okay, and this is infinity, this is infinity, this is infinity. Try to make a straight line because it looks good. This is infinity, this is infinite distance. So this point is, if it is O, this point is P, then this distance is R. Okay, then this distance is R. This is important thing. Now we are going to calculate the potential due to this point charge at point P, which is at a distance R from that point charge. Then how are you going to calculate? So previously you have learned that what is that potential? It is the potential of a point. What is that? The formula that is work done by the charge. Okay, so we need to calculate the work done first, and then we are going to do such things. Okay, don't worry about these things, we will calculate them. So if this is a point charge Q naught, okay, this is a point charge Q naught, and this is a point A, this is a point B. Okay, this is point A and this is a point B, like in the previous classes which we have. Since it is a positive test, it is a positive charge, it is also a positive charge, then the direction of force is like this. The direction of force is like this on this test charge. Now you are going to bring this test charge from this point to this point. Let us just calculate these things. So B is at a distance x from Q, and this is dx. This is a infinitesimal distance dx. So you can see that you are bringing this test charge from A towards B. That means you are covering a distance dx. And if dx is like this, is pointing in this direction, then f is pointing in the opposite direction. That means the direction between f and dx is 180 degree. You can actually see that. So we are going to write all these things into a statement. So just understand such things. Let us consider. Let us consider a point charge Q. A point charge Q, mostly positive. You can denote it or you can mention it. So it should be positive. Okay. Let us consider a point charge Q at point O. At point O, let P be at a distance. P be at a distance R from O, at which we want to calculate the potential. At which we want to calculate the potential. Calculate the potential. Okay. So, what is the thing you need here? You need to plot the force between these things. Okay. Let us place a unit positive test charge at somewhere in that line. Let that point be x at A. Okay, let that point be A. Any point. You can choose any point on this line going towards infinity. So we are now going to calculate the force. So as you know, it is a simple equation of force. What is that? It is electrostatics force. So we are going to use Coulomb's law for this. So what does Coulomb's law say? That this force is proportional to the multiplication of the magnitude of this charge and is inversely proportional to the square of the distance between them. So you can actually see that what would be the equation of force? The equation of force should be F is equal to 1 upon 4 pi epsilon 1 upon 4 pi epsilon naught q naught by x. Oh, sorry, I have denoted it wrong. That point A is at a distance x. Okay, this point is a distance x, and this is infinitesimal distance dx. Okay, I have committed a mistake here. So this is infinitesimal distance dx. So if the distance between them is x, then the force between the electrostatic force of repulsion between them is F is equal to, given by Coulomb's law of electrostatics, 1 upon 4 pi epsilon naught q naught by x squared. This is your equation of force. This is important thing. Okay. Now you are bringing that q naught closer to q. You are bringing q naught closer to q. Okay. So by what distance you are giving it closer? Let just consider that, assume that you are bringing it closer by a distance dx, and you are calculating the work done. In that you are doing work against the electrostatic forces. So you are doing work against the electrostatic forces. We are calculating the infinitesimal work done for this infinitesimal distance, and then we shall be integrating the whole equation, for which you will find the electric potential due to a point charge. So okay, so this is our force. Now we know that work done, in order to doing work from A to B, we denote that work done from work done in bringing Q naught from A to B is, so that work done must be dW. Okay, a small work, because the distance is very small. So what should be that? F dot dx. As we know, for work done is equal to force, the dot product of force and distance. So you can see that the force is along this direction and the distance is along this direction, that means the angle between them is, if it is dx, it is force. So what is the angle between them? Theta is equal to 180 degree. So you can actually write f dx cos 180 degree. Why I am writing cos? Because the dot product says so. The result of dot product is that f dot dx gives you f dx cos 180 degree, which is minus f dx, minus f dx. So are you getting it? Yes. So dw is equal to minus f dx. Now you are going to integrate it. Now you are going to, so you got the work done when you brought the charge from this point to this point. That means you brought the charge from x to dx. Now you are going to bring that charge from infinity towards r. From infinity towards r. That means you are going to integrate it. Okay, so dw, let us integrate it. Integrating to get the complete work. Integrating to get the complete work. So how are we going to do that? So you integrate this from 0 to w, or you don't require it. Okay, then you leave the negative sign outside f dx. So the whole work is done from infinity to r. You are bringing the charge from infinity to that specified distance at which you are going to calculate that potential, like we have discussed in the previous classes. So this is important thing. This integration is an important thing. So I think that you are getting it. So let us just lower the camera so we can utilize the remaining space. I have to just bend my waist a little bit. So this integration will give you w. Just focus here. The negative sign is here. Try to plot the point here. 1 upon 4 pi epsilon naught q naught upon x squared dx. It is infinity towards r. So from this equation you can see that this term is constant and these two terms are constant. So you can actually take them out of the equation. So take them out of the equation. Minus 1 upon 4 pi epsilon naught q naught integration from from infinity to r, dx over x squared. Okay, dx over x squared. So I think you are getting it. So we are going to integrate it. As you know, the integration of x to the power n, it is x to the power n, leaving aside some certain conditions. So it is a definite integral epsilon naught q naught. So it will be 1 by x. It will be 1 by x, minus 2 plus 1 by minus 2 plus 1 minus. This is what your integral should look like. Okay, let me go a little bit low. Can utilize some more space. Okay, so this negative thing, they get cancelled out. So 1 by 4 pi epsilon naught q naught 1 by x infinity towards r. So you just put these formulas, this in formula. 1 upon 4 pi epsilon naught q naught 1 by r minus 1 by infinity. And you know that 1 by infinity, it is 0. It is 0. So you are left to it. So let me use the space on the left side. Don't worry, it won't affect your formula. You just continue on the as you write in your copy. Okay. So what is the work done? it is 1 by 4 pi epsilon naught q naught by r. This is your required formula. This is your required formula. Okay. After doing such analysis, we found out the formula for work done. So our work is not over, as we are going to calculate the electric potential. Okay, we have calculated only the work done, but we haven't found the electric potential yet. Okay, so let us just give you a bigger overview of this solution. Okay, because I am going to rub something off from this point. Okay, so I assume that you have completed these things, and this work done will continue from here. Okay, this is a continuation from this equation. So I assume that you have written all of these things, or you can take a good screenshot here. So just now let us calculate the potential. Now let us calculate the potential. I am going to use the left space, that is left portion. Given a good space, which I got a good space in here. So we are going to need this equation. So we know that potential at distance r is equal to work done by that charge, by work done divided by that unit positive test charge. So from this point you have gathered that work done is q naught by r divided by r, it is v. So v, as you have calculated, it is simply 1 upon 4 pi epsilon naught q by r. This is your required equation. This is your required equation. See, q naught gets cancelled out, so you are left out with this thing only. So I hope that you have understood all these things, because I am going to rub these things now, because I will be giving you a small analysis of this equation. So let me rub it. We are keeping only the equation only, that is v. So you can see that from this equation, so you can focus on this part. You can see that from this equation. So I shall be writing the equation again, need not worry. So v is equal to 1 upon 4 pi epsilon naught q by r. This is your equation. Okay, this was your equation. Now we are going to analyze it. Okay, so you can see that for a given charge q, you don't need q naught. You don't need q naught in your equation. It was only given, or it was only used to calculate or derive to the formula. We reached to the formula by the help of q naught. Okay, and that thing got cancelled out in the mean process. So you can see that for a given charge, at source charge q, we can actually calculate the potential at a distance r, and this potential is inversely proportional to the distance. This potential is inversely proportional to the distance at which we want to calculate the potential. So this was our analysis, and now we are going to present it graphically. I think this portion will be enough for it. So we are going to start the graphing of this equation. So yeah, and so you can write the analysis here, that v is inversely proportional to r. Okay, this is your analysis. You have to write it as a capital V, like a bigger V. So you can give a design like this. Don't get confused. Don't consider it as the velocity. Okay, don't consider it as the velocity. So if we draw now, before going to that, just you need to draw your attention into the part that at infinity potential is 0. At infinity potential is 0, because you place infinity at this point. Okay, at r is equal to infinity, when you place that, anything by infinity, it becomes to 0. Not anything by infinity, so any number by infinity will give you 0. Okay, so potential at infinity is 0. You can actually note that potential at infinity is 0. You can note that, it is not that necessary. You can actually see that from here. So what is the graph? What is the graph? Try to make straight lines. Try to make straight lines. Since it is, this is your infinity, it is going towards infinity. Okay, so the distance increases, the potential decreases, or when the distance decreases, the potential increases. That means when we are at these portions only, the potential is very high. Okay, the potential is very high. And now when we increase distance r, when we increase distance r, it tends to, okay, this thing must be close to the graph, okay, to the x-axis, because v is getting 0, or v is tending to go towards 0 as we increase the distance. This is r, this is v. Okay, this is r, this is v. When we plot potential v against distance r, we get this such a graph. Okay, this, and it is quite similar to the electric field versus r graph. If you remember such things, if you remember that thing, you will find that it is quite similar to that electric field graph, okay, versus r. So we are going to, in the next lecture, we shall be drawing the relationship between V and E. Okay, V is potential. Okay, let's draw it like this. V is potential. So, and E, we are going to draw that relation. So you can see that when this approaches infinity, this will be getting very close to this axis. So this distance will becomes 0, which will give you that V is 0 at such points. At points very far, at points we can only define those points as infinity. Okay, so we are going to do some more things in this lecture, so I rub these things off. So what are we going to do now? As we have already done, that we are going to calculate these things for a dipole. Calculate these things for a dipole. Okay. Electric potential due to a dipole. Okay, I don't have to write all of this again, but you have to write all of these things again, because I can rub it and you cannot. You have to write all these things again. So electric potential due to a dipole, due to a dipole. As you all remember what is a dipole. So what is a dipole? A dipole is a system of two charges. Okay, what are those two charges? The charges are equal in magnitude, but they are opposite to each other in their nature. If one is a positive charge, the other should be a negative charge, and the distance between them is very small. The distance between them is very small. So this is a dipole. And recalling something again, so let me just draw these things to an upper level. So recalling something up, what is an ideal electric dipole? Do you remember those things, that what are the conditions that makes an ideal electric dipole? So in an ideal electric dipole, the magnitude of that charges is very large. They tend to go infinity. They tend to go infinity, and the distance between them is very small. That tends to become 0. And if those two conditions are satisfied, then the dipole is called an ideal electric dipole. But until then, up until then, we are just going to consider a dipole only. So let me just use a ruler to give you a better say of things. So this is a ruler. I'm going to use this side. Okay. draw such thing patiently. Okay, due to a dipole at an axial point, you can mention at an axial point. So q minus q, this is a dipole. The distance between them is a to a. You can actually write, okay, this is O. This is A. This is A. A. And you are going to calculate potential due to this dipole at a point distance r from O. This is your point P, not P. Let it be M. Okay. So from the center, OM distance is R. So you are going to calculate the potential at M. You can actually take this distance, this to be here, this to be here. So this distribution does not change your answers. Okay. You can take M to this side, M to this side. This does not change your answer. Okay. So now, what is this distance? What is this distance? If it is r, if it is a, then this distance is r minus a. This distance is r minus a. And if it is r, if it is a, then this total distance is r plus a. You can actually analyze this from the formula. So just let us draw the statements. So we can write from this side. Let us consider a dipole consisting of charges q and minus q. So you can see that the magnitude is same, q and q, the magnitude is same, but they are of opposite nature. Distance between them is O, or the length of the dipole. You can write anything, distance between them then is equal to 2a. So you can ask, sir, why the distance is 2a, not a? Because when we are calculating things from the center, the distance become a by 2. Okay, and that's does not look that good, because when you have 2a, you divide it by 2, you will get a. So it's a whole thing. So let m is an axial point. M is an axial point. Okay, M is an axial point at a distance r from O. M is at a distance r from O. So you are getting all of these things. Yes, you are getting. So we are going to calculate. We are going to calculate potential at M due to dipole. Okay, due to dipole. So for this dipole, you are going to calculate the potential at M due to these charges separately. So for charge Q, since a potential is a scalar quantity, we are going to calculate the potential for this charge at point M, and then you are going to calculate the potential for this charge at point M, and then add them up. So for charge Q, BQ, okay, that will be BQ. It is 1 upon 4 pi epsilon naught Q upon, what is the distance? R plus A. R plus A. Similarly, 4, you can name it equation 1. 4 minus Q, V minus Q. Okay, V minus Q, denote it as V minus Q. It is 1 upon 4 pi epsilon naught minus Q by, what is the distance? R minus A. What is the distance from minus q and m? It is r minus a. So name it equation 2. So you get two potential, that is vq and v minus q. Why is this minus? Because it denotes the nature of the potential. Okay. So net potential, since these are scalar quantities, should be v. Okay, net potential v should be the addition of vq and v minus q. So you can actually mention it here, since potential is a scalar, they, so sorry, like potentials are scalars, they can be added algebraically. Since they are scalars, you can add them algebraically, just as you add 1 2 3 4, so you can actually add them. Okay, now just plot the formula, you have derived here. So it is 1 upon 4 pi epsilon naught q by r plus a. This is plus, this is minus, that will be minus 1 upon 4 pi epsilon naught q by r minus a. Just continue from this side. You see that these things are common in both the terms. So q by 4 pi epsilon naught, you get 1 by r plus a minus 1 by r minus a. This is the equation. Okay, we have to continue that. So take LCM of these things. This thing come to this side and get multiplied with 1. This thing goes to that side and get multiplied by 1. So you get q by 4 pi epsilon naught, it is r plus a into r minus a minus r plus a. Okay, so just try to calculate them, which will give you q by 4 pi epsilon, q by 4 pi epsilon naught, c r minus a minus r minus a, c r minus a minus r minus, that means r's are getting cancelled, so r, so it will give you minus 2a by r square minus a square, minus 2a by r square. So it is a plus b into a minus b thing, so that is r square minus a square. So it is your general formula. This is your general formula due to a dipole. Minus q 2qa by 4 pi epsilon naught r square minus a square. This is your required formula. So you can get that formula. Now if y it is negative, you can also check that why it is negative. So if q is on this side and minus q is on that side, then it will be a positive thing. Okay, so why it is negative? Because it is numerically higher, because it is closer to m, it is numerically higher, so it is negative. You are going only to calculate the magnitude, then you have to cancel these things. Okay, so let us now analyze something. If it is 2qa, so you can actually write it is 2qa by, in magnitude, epsilon naught r square minus a square. Okay, r square minus a square. This is 2qa r square minus a squared. Now you know that q is here, 2a is the length of that dipole. Q multiplied that length of the dipole will give you electric dipole moment. It will give you electric dipole moment. And if a is very small, so you can write it like it, p by 4 pi epsilon naught r square minus a square. Okay, P is the electric dipole moment. So I think you can see it there. So I am going to rub all these things off as I think you have completed these things, because I am not finished with that formula. I am not finished with that formula. So you can write that V is equal to P by 4 pi epsilon naught. So take it a little bit further upward, r square minus a square. If a is very small, a is very small, or a square is very less than r square, then your v becomes p by 4 pi epsilon naught r square minus a square is almost equal to r square. Okay, this is your required formula at an axial point. So at an axial point of a dipole, what is the formula? V is equal to P by 4 pi epsilon naught divided by r square. This is your formula. Okay, so now we have found out that the dipole has a potential at m. So, and you already, why you know that it is negative? Because the negative charge is closer to point m. So the potential due to, or the negative potential at m is higher, and since q, that is a positive charge, is far from the point m, so the potential at point m due to the positive charge q is lesser. So when you add them, the negative charge dominates. Okay, when you add them, the negative charge dominates. So that's why that thing is minus. Okay, so when you are going to ask about the magnitude, you can actually only repeat that formula. Now this thing will be derived if you had considered q at this place and minus q at this place. Okay. So if you had interchanged their position, you have been arrived at this formula directly. So now we are going to we are almost at the end of our lecture. So we are going to calculate the electric potential due to a dipole at any equatorial point. Okay, at any equatorial point is our last step. So at this point also we have to rewrite all of these things. Okay, no, you not have to write all of these things. I am going to just make a few changes at an equatorial point. Equatorial. So you could ask me that, sir or Mr. Teacher, why only we are considering, even if for a dipole, only the axial point and the equatorial point? It is a very valid question. So why we are not considering them, or why we are considering only those points? We can also consider any point. Okay, we can also derive or get close to formula. So no need to worry. Someday when I have lesser work, I will give you that formula. So similarly, draw a dipole. Draw a dipole. Irrespective of their position, you need not worry about their position. The distance is 2a. Okay, the distance is 2a. This is O. The distance is 2a. And these distances are a. This is a. This is a. This is 2a. A. So similarly, m is that point at a distance r. M is that point. So this is point M that distance is r, this is r. Okay, so let us consider a dipole consisting of charges q and minus q. Distance between them is 2a. M is an equatorial point. This is the last clip of our lecture, so don't worry, we are going to get finished soon. So M is an equatorial point at a distance r from O. Okay. So we are going to calculate the potential at M. So similarly, in just like we have calculated the electric potential due to a dipole at an axial point, here also we are going to calculate the potential at M due to this positive charge, and we are going to calculate the potential at M due to this negative charge. Okay, so for Q, so to calculate that potential, we need to calculate that distance. Okay, we need to calculate that distance also. This is R. So how are we going to calculate this distance? This is A, this is R, this is a 90-degree angle as we have known. So this distance, let this be A, this is B. Try to make it as straight as possible. Okay, so from triangle AMO, from right angle triangle, okay, mention it. A right angle triangle AMO, AM squared is equal to OA squared plus OM squared. So you need AM. Okay, you need AM square root over OA squared plus OM squared. Just put those things. Or what is OA? This is A square plus what is OR? It is R square. Okay, this is your AM. Since AM is like this, BM is also like this. The same thing. Okay, the same thing. This is also R square plus A square. This is R square plus A square. Okay, so VQ equal to potential. So VQ is the potential due to this charge at point M. So what should be that thing? 1 by 4 pi epsilon naught Q by R, or the distance. The distance is your R square plus A square square root. This is your equation 1. Now similarly V minus Q, it is 1 upon 4 pi epsilon naught. It is minus Q since it is a negative charge, R square plus A square. This is your equation 2. So what is left? You have to add them. So adding 1 and 2, the net potential is VQ plus V minus Q. So 1 by 4 pi epsilon naught Q by R square plus A square minus 1 by 4 pi epsilon naught Q by R square plus A square. Okay, these are the same things. Okay, these are the same thing. When you add them, this negative comes into play. So V is equal to 0. They get cancelled out. So at any equatorial point, V is equal to 0. Potential is 0 because its potential is cancelling its potential. It is a positive potential at A, it is a negative potential at point M. They are equal in magnitude, so they are cancelling them. Why they are equal in magnitude? Because the charge is the magnitude of the charges are equal, and the distance between the charges and that point M is equal. So this is the reason why this is getting cancelled. So VEQ is equal to 0. So your potential at any point on the equatorial line is 0. So you can write the statement: the potential at any point on the equatorial plane or line, you can say equatorial line or equatorial plane, is zero. It is zero. So this is your statement. So this is your statement. You can take a good screenshot of the last thing. So today we are going to start this lecture today, and we shall be continuing tomorrow. So if you have any doubt, you can actually contact me. I have given my contact details in that description box of the video lectures. You can also comment, provide a good comment or any comment in my videos, which I shall be giving you a good response. So up until then, keep practicing more and more problems, and if doubts, you can connect to me. So up until then, take care and goodbye. Thank you.